All right, Phantom's model. Let's talk about the actual linear regression t-test. Let me first tell you that these first 3 paragraphs kind of yammer on about stuff, but I think I can make it make more sense with something better. Let's talk about this. This whole entire semester, we have learned how to interpret, and is that inference, and do a problem for inference. And so the first thing we learned how to do for inference was we always take a blank and we infer to the blank. What are we always taking? Sample. Good. We are always taking a sample and we are inferring to the population. Very good. Okay. Well, our very first test that we did took a sample proportion. That's what the notation looked like. Let's kind of summarize some notation. P hat is a sample proportion. And when we summarized it, or I'm sorry, made an inference to the entire population, that notation was or is a straight up capital P. All right, let's just kind of do some notation. Next, we did what? After proportions, we did means. What's the notation for sample mean? X bar. And then we generalize that to the whole population, and that would be represented by a mu. Good. All right. The final statistical test that we will perform is about slope. So we will be taking data, and we will take a sample slope, notated by a lowercase b. And we will infer the slope for the relationship of the entire population. So it's the slope of the relationship between 2 variables that we are inferring for the entire population. And that is going to be represented by the letter capital beta. And again, a linear regression test is about the slope of the relationship between 2 variables, x and y. Okay, so that's what we are doing today. We're going to practice a whole Phantoms model, but first let's talk about the hypotheses statement. The null hypothesis, of course, there being no linear relationship, so the slope would be 0. If there is a linear relationship, we have a not equal to happening. Okay? Now, FYI, I have seen an AP free response question where a curveball was thrown. It kind of threw a lot of the nation off, actually. They had a slope. They had a slope of 6 that they were wanting you to compare your slope against instead of a slope of 0. Okay, so that was kind of tricky. I will show you that problem later so that you can see that it has happened to not be 0 because they asked to compare to a specific slope, not just is there a linear relationship. When that happened, by the way, on the grading guidelines, they ended up grading it such that if you put 0 in there and did your whole entire test appropriately with a 0, you only missed a half a point, maybe a whole. I think the most you could get would be a 3. You lost a half of a point, but out of the 4 on the free response, the most you could get was a 3. So it didn't just totally kill your whole problem and give you nothing. Because a lot of people were taught just to do the 0 there. All right, test statistic is this b minus a hypothesized value. What does this b represent? What slope? Sample slope. Very good. And what is the hypothesized value? In this case, it is the 0 over S sub b. What's S sub b stand for? Standard deviation of. Correct. Okay? Now, another type of degrees of freedom. We have 3 so far. This is the last and final one. We know that on all t-tests, our degrees of freedom are n minus 1. When we did a chi-squared goodness of fit, our degrees of freedom were categories minus 1. I don't know why I put parentheses on that. When we did a regular chi-squared, it was rows minus 1 times columns minus 1. And this final one for a linear is n minus 2. You know why it's n minus 2? I'll tell you why. We have some more added variability. We have more variability. You know why we have more variability? Because it's 2 variable problem, not just one. Variability in the x direction, variability in the y direction. 2 sets of variability, so it's n minus 2 instead of just n minus 1. Does that make sense? Okay. All right. Your assumptions are going to be saved for tomorrow. You see that they have a mnemonic device line, and they're kind of like all new. They're not random, independent, large enough. They're kind of a whole new ball of wax, so we're going to save that for tomorrow. We're going to do a calculator test right now. So turn over the page and let's do this phantoms model right here. Okay. Computers seem to have invaded every aspect of our lives. Many studies documenting the varied effects of computer revolution have dealt with the work environment of people who spend a substantial amount of time staring at computer monitors. Image quality of monitors is an important characteristic. You know, HD display, what else? The retina display, all that kind of stuff, okay? That affects, among other things, the extent of eye strain and the work efficiency. Some data gathered in the historic age of 1991, so this is definitely an old situation. Back then, we were still, us in junior and high school, we were still in big-time pixels. I mean, like big old pixels, bigger than what you see on, like, Minecraft. I was big-time lucky. When I went to college, I had a word processor that probably was about the size of this backpack. I'm not kidding. Yeah. Okay, so my word processor was about the size, I'm holding it, was about the size of this thing right here, so it was huge. It did have a little 3x3 light-up screen that I could see what I was typing before I pressed enter and it printed. Okay, so that was it. It even had a 3x3 little 3x3 disc, hard disc, which was not floppy, even though we called it floppy. It wasn't the 5x5 floppy disk that actually flopped. It was a 3x3 hard disk. That was big time. Okay, so this is definitely, so that's what's going on at this age. So there definitely was a big difference in the extent of eye strain versus and the work efficiency with the image quality. Okay?
What was the minimum technology? 2000?
I don't know.
I think it's
All right. So here we go. Some data gathered in the ancient age of 1991 reported on an experiment in which image quality and average time for a group of subjects to read the certain passage in seconds was determined. Okay, see if there is significant evidence. That means run a test and get a p-value. That's what significance means. Run a test and look at the p-value. Okay, now let's look at this. Time in seconds versus image quality. Which one of those is the explanatory variables? Which one's influencing the other?
image quality.
Image quality is actually the one that's influencing the time. That kind of goes against a typically, frequently, time is the X variable because it's just the input and then you see what happened at that time. But in this case, our image quality is the input and then we see what the time response to read the package was, or the passage was in reference to how, what the quality of the image was. All right, so let's start running our test. We're going to do everything except for the assumptions, and we will start with the parameter of interest. What is our parameter of interest? What are we going to finish making an inference about? Yes, about the relationship. But more specifically, our parameter of interest is beta. That is the slope of the relationship. That's what our linear regression t-tests do. Slope of the relationship between image quality and time to read the passage in seconds. I need to somehow, like, really hone in that it's about a population for all. If you don't do this part, you're kind of skipping the part of the description. You need it for all what? I'm pretty sure it's for all people who spend a substantial amount of time staring at computer monitors. That's who we're wanting to make an inference to. And for time saving, I'm going to do that. But you certainly would not do that on AP. All right. So there's our parameter that we will be making an inference about. What is the null hypothesis? Theta is 0. No linear relationship is what that is saying. Our alternative, theta is not 0. All right, the assumptions come next, and that's tomorrow. So now name the test. What is it? Linear regression t-test. All right, now we want to get the data. We want to have the t-value, we want to have the p-value, and we want to have the degrees of freedom. So I'm going to teach you what to do in your calculator. In fact, for time's sake, I mean, unless you just, you can go ahead and put that in, but I have it up here if you want to just follow along. I'm going to go and put my information in. Now, I'm going to tell you that, my bad, you know what I did when I put this stuff in? I fell into my old habits, and I actually put list 1 is the top line, and list 2 is the bottom line. And so what potential problem is that? What do I really have to now make sure I keep straight?
The X and Y.
The X and the Y. Yeah, because that's unusual. Normally, our X is not list 2. Okay, so my bad, I kind of mixed that around. But so look at what I got here, and let me tell you how to fix that. If you do that, then you don't want to have to rewrite the whole thing. So, I got my data in here. Let's go run the test. Where do you think it is? Stat. Over to test. Go up, and I want you to just glean a look at the fact that you know everything on this page. Tomorrow we will be doing the linear regression t-interval, with the exception of 2 things. Two sample F test, you're never going to learn, and ANOVA, you're never going to learn. So I remember back when I told you, look at this list, you're going to learn the whole thing, and I've got some, you know, deer in the headlight type looks. You now know it all except for those 2 things, so congratulations. So here we go, linear regression t-test. Do you see how I accounted for my boo-boo and putting my lists in? Right there, I say that list 2 is where the X values are located, and list 1 is where the Y values are located, because my bad, I put just kind of fell into old habits. Put the things in backwards. All right. Not equal to, you do not have to put a regression equation in, and it's actually going to compute that for you. Okay? So let's go down and calculate. Okay? There it is. T-value, P-value, degrees of freedom, A and B. Let's see here. 9.64. What is that? Y-intercept or slope?
Y-intercept.
9.64. Y-intercept or slope? How do you know it's a y-intercept? Yep, because up here it's kind of like the key. The A value is the plain y-intercept. Okay, how about B? B is the
Slope.
Because up here it tells you that B is the variable, the number in front of the X. So that's why you knew B is the slope. Okay, let's put our T value and our P value down right here. Here we go. Negative 3.096, 0.0212, degrees of freedom, 6. All right, so what is our situation going on? Our p-value of 0.0212 is less than alpha of 0.05. So what's our decision?
Rejecting.
We are rejecting. Now, for just time's sake, what are we rejecting? We are rejecting that. Well, we're rejecting that there is no linear relationship between, we were rejecting the null hypothesis, and the null hypothesis says there is no linear relationship between blah, 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 and blah, 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 image quality and time for all those da, 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 da. Therefore, I have what? Statistical evidence of a linear relationship. That's what we're getting at. Not just a relationship, but a linear relationship between blah, 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 and blah, blah, blah for all those people who spend a lot of time at the computer monitors. Okay? All right. That is a phantoms model without the A. Now, when you look at your homework, which I don't have, let's look at that first. Oh, wait, yeah, dude. It's right here. Okay, we're not done, so don't you be packing up. I got 2 things I need to talk to you about still.
Hold on.
Okay? So turn here. I have 2 things still to talk to you about on this. Number 1, give statistical evidence as to whether or not there is a linear relationship in the data below. So what is that telling you to do? Run a phantoms model without the A. Okay? You can do this without any assumptions. A phantoms without the A. Now, you don't have individual pieces of data to put into the calculator. So let's talk about this. You need a t-value. Where is it? You need a t-value for the slope. What? Okay, this is the line about slope. The slope is 4.15, that's true. What's this number right here? 1.3, I'm going to call it because I'm going to reference it in a minute. Standard deviation of the slope. What's this right here? It says t-ratio. What does that mean? That's the t-value of the slope. So when it comes time to put those numbers down, there you go. T-value. Done. And what's this next to it? That is the p-value for the slope. So based on that, you're going to end up what? Rejecting. Okay. So you will do a full phantoms model with that. Now, I have 2 things to talk to you about in these last few minutes. No, you don't need a calculator. It's a conceptual idea. So, I got 6 minutes. So I got 2 things. I got 3 minutes each. So here we go. First thing is standard deviation of the slope. You guys already located it as 1.3. Okay, so let's talk about standard deviation of the slope. We kind of addressed this yesterday, and so I just want to emphasize it again today. You can see from this picture that this line here has a slope of 4.15. That came from 1 sample. Do you feel confident telling me what the slope is for the whole population just from that 1 sample? No, better not. Okay, so there should be some variability, some uncertainty, some wiggle room. And that wiggle room is your standard deviation of the slope. So, what we have here, it could be steeper. What's a reasonable amount of wiggability?
2 standard deviations.
2 standard deviations. So if this slope here ended up being 4.15 plus 2 standard deviations, then I'm going to get somewhere around 6.75. Okay? So then I'm going to say, if my slope is that steep, I'm not going to freak out. Okay? What else could happen?
It could be lower.
It could be And what would it look like?
It'd be a little flatter.
Flatter. Okay, so this would be 4.15. And then what? Minus 2 standard deviations. It might be somewhere around 1.55. Just FYI, a little glimpse into the future. What happens if my
Failed to reject.
slope could go from a negative slope up to a positive slope?
There's no.
Then it could be
No.
It could be 0. If it's going from negative up to positive, there could be a 0 slope. We'll talk about that tomorrow. All right, final thing. Here it is right here. You don't have this, I have it. Think of this distribution of, look at here. This is a talk about the standard deviation of residuals, okay? And here's what it looks like. Think of a 3D normal curve. You've got, this is your prediction line right here. The standard deviations of the residuals tells you about the observances around that prediction line. You will have 68% of data within 1 standard deviation around the prediction line. You see that? You will have 68% of the observances within 1 standard deviation, up and down. How about 2 standard deviations? If I go out 2 standard deviations, okay, then that means I'm going to have 95% of observations contained within 2 standard deviations. So we now, see this right here? We now have the ability to quantify what an outlier would be, where an outlier would be. And got 3 minutes, so on this front here, here's what it looks like with this particular problem. This is a problem about the cost of a battery and its power in amps. Do you ever wonder if a battery is more powerful because it costs more? I do, because I go to the store and I'm like, why is this one more? Okay, well, I wonder if it's going to last longer and actually be more cost effective. Okay, so look here. Look here, look here, look here. Here is your prediction line. Where is the standard deviation of the residuals on this? Computer printout. Computer printout, sorry. Right here. This is the standard deviation of residuals. This is the variability of those observances. It's 116. So guess what? You see this residual plot here? If I go up to like 116
68%.
and go down to 116, 68% of all of the observances are falling in that range.
That's a 3D curve.
Okay? And now let's go out 2 standard deviations.
5.
How much is 2 standard deviations up? 116 times 2. 232. If I go out to 232, how much percent is in there?
92.
95%. Okay, is in there.
Julie, that's rude. Don't say that about me.
So then you can tell that